We continue with constraint optimization. Consider the general constraint problem. Minimize f of x subject to a number of equality and inequality constraints h I of x and g I of x. H I of x are the equality constraints and g I of x are the inequality constraints. So here we form the Lagrangian function, converting from the constraint problem to unconstrained problem. The Kern-Tucker conditions says that assume f, hi, and gi are continuously differentiable, and x star is feasible and satisfies the constraint qualification conditions. The condition for local optimality of x star is there exists lambda I star and mu I star greater than 0, such that the gradient of the Lagrangian function at x star is equal to 0. And also mu I star times gi at x star is also equal to 0. And this is for all I. Lambda I and mu I are the Lagrangian multipliers, so also called dual variables, and as opposed to the primal variables x. But let's take an example. Maximize x1 to the lambda times x2 to the 1 minus alpha. Subject to p1 times x1 plus p2 times x2 is equal to w. So from here we form the Lagrangian function. The additive function goes into the first term and the constraint goes to the second term. With lambda as the Lagrangian multiplier. So taking the derivative and letting them equal to 0, we have three variables, so we have three derivatives. So let them equal to 0. We have three equations, and then divide by 1 by 2. We have this and that. And from the third equation, we have this. And replace this back in there. Then we have this one, this equation. So from there we get x1 and replace x1 back. In here we have x2. Okay, now let's talk about the duality theory. Consider the constraint optimization problem. Minimize f of x subject to the inequality constraints gi of x less than or equal to 0 for all I. From there, we form the Lagrangian function. With given multiplier vector mu, minimization of Lagrangian function with respect to x is called the relaxed problem. The solution of the relaxed problem defines a function w of mu, and this is called the dual function. The dual function mu, the dual function w of mu is actually this, minimize the Lagrangian function with respect to x. The dual problem is maximize w of mu with mu greater than or equal to 0. Or maximize of the minimization problem with respect to x and minimize the Lagrangian function. The weak duality theorem says that for any mu greater than or equal to 0, the dual function is the lower bound for the optimum f at x star of the primal problem, with all mu greater than or equal to 0. Theorem: if there is a pair x star and mu star satisfying the conditions, there are 3 conditions, then x star is the global optimum for the primal problem. And you may notice this actually x star, the Lagrangian function are x star, and with other constraints as well. Example. So let's say we need to minimize this objective function x1 squared plus x2 squared, subject to a number of inequality constraints. Then from there we have the dual function. We can separate the dual function into several minimization functions regarding with respect to x1 and x2. And since mu is greater than or equal to 0, so taking the derivative of this function and the other function and let them equal to 0, solving, and we get this. And then we place back x1 and x2 into the dual function, we get w of mu. And the maximum of the dual function is reached for mu stars equal to 4. And when we have w at 4, dual function at 4, and f star is equal to 8 at x1 stars equals to x2 star equal to 2. And here we have the explicit representation of the dual function. Maximization of the dual function in general is tackled by the numerical method. Basically, we start with an initial value mu 0. So we have basically have mu 0, mu 1, mu 2, etc. And we solve the relaxed problem with this mu, basically mu 0. And later on we have mu 1, mu 2, etc. And given the solution x, k of the relaxed problem, we compute a search relation sk and a step length alpha k, and update the multiplier. So basically it is mu k of 1 is basically equal to mu k plus alpha k times sk. Alpha k is a step length, and this is actually the relation. And that is added to mu k. And if this is negative, then the max function actually would return 0. Then you increase k. Basically, you would do the same thing with mu 1, and then mu 2, and then mu 3, etc.